All right. Whoa. Uh-oh. Hold on. There we go. Gotta get back again. And back to me. All right. Welcome to another IAEI News Live. My name is Thomas Dimitrovich. And today is Tuesday. Welcome back to another IAEI News Live. My name is Thomas Dimitrovich. Today is Tuesday. It is Tech Tuesday, and we're ready to talk about feeders. Today's technical topic is feeders. So I want you to get out your 2023 code book. I'm going to be using NFPA Link. I'm going to use NFPA Link, and I think I got to bring my volume down a little bit. Get your coffee. Make sure you have your coffee, and we're going to talk about Article 215 is where we're going to go. So it is Thanksgiving weekend. Hey, Laurel, thank you for joining. Yeah, had to fix the echo. Sorry about that. Yep. Yeah, it's gone now. You know, Nihad, I've got two cameras set up now. I'm testing. I'm going to be doing an interview for an individual here shortly, or soon this month, or no, in December. And I wanted to have a camera set up here. And I have my camera set up on this side over here. So I have two different cameras now so that I can figure out how do I switch and how do I do an interview. So that's what I was doing. And it was bringing in the volume for both. So I got both cameras set up, and that's the way it goes. Travis, welcome. Travis, welcome to Travis Holderman. Good morning, and welcome to an IAEI News Live. Today we're going to talk feeders, and we know we spent a lot of time on services, which I'm still working. I did a for the West Virginia chapter of the IAEI. We had 8 hours. 8 hours on services. And I'll tell you that doing that presentation was phenomenal for me because I realized there is a lot about services. We were doing overhead and underground service connections. We were in overhead services, and I'll tell you what, Felix, very good to see you again, my friend. Thank you for coming in. We've got Columbia in the house. So Felix, we did, geez, oh man. Everybody calls right at 12 o'clock. I don't know if it's planned that way. So it is Colombian roast. This is coffee. I brought back, I'd have to go back and get the bags, but I brought back a whole suitcase full of Colombian roast, and man, it is absolutely phenomenal. Oh, good morning, Steve. Welcome to IAI News Live, and I hope you got your, hey, Thanksgiving, happy Thanksgiving, David Engelhart. Happy Thanksgiving, brother. I really appreciate you and all you do, as well as everybody else who's joining in. We're letting people filter in right now. But yes, this is Colombian roast. I'd have to go back. I got so many different types. And I don't know if you can see it. You might be able to see it in camera B. You see this right there? This is a coffee grinder. This was my grandmother's coffee grinder from her store. It is an Art Deco type of look to it. I have to replace the cord on it, but I am going to be using that because I brought a lot of beans home from Colombia, and we're going to be using that to grind. So you got to love it. And David Englehart, thank you, and happy Thanksgiving to you as well. All right, so let's do this. We're going to start. Let me get 215. Now I'm building out the slide deck for this. So I am definitely... Travis, I'll tell you what. Travis Holderman, I'll tell you what. So I did 8 hours, and I did 8 hours on services, but the way the class went, what I really enjoyed was we had a lot of dialogue amongst the people in the classroom. That is what made that whole event worthwhile for me. It was very eye-opening. It was engaging, and teaching to me is you're telling a story and you're getting as many people engaged as you can. So it's a lot of standing on your feet, and it's great to break it up if you can with multiple presenters. We had just me and everybody else. It was just a good meeting. It really was. I'm looking forward to Shock Week too, brother. All right, so let's talk about. Let's see if I can do this. There it is. We're going to hit Article 215, feeders. Feeders is it's a pretty. If you look at Article 215, we're going to go through Article 215, but we're going to end up going to a lot of different areas within the book. And I wish I had my hard copy, but I'm going to be using NFPA link, and I do need to get my other monitor. I got to bring the other monitor down here. That way I can have everything set up. I'll have another monitor over here. But in any case. Oh, man, thank you. I've got to mute the Blackmagic design. Oh, here it is. Off. Boom. Now I don't have to worry. So even if this is unmuted, I'm not going to get any audio from the Blackmagic. So the Blackmagic is my thing. Laurel, thank you. Echo, echo. I apologize for all you out there. No, it's Dan. It's not picking up the speakers. I have 2 cameras running, and I'm bringing it through an A10 Mini Pro, which is a Blackmagic design. I'll show it to you. It's this thing right here. So there is a button on here that says bring the audio from this separate camera, and the separate camera is this camera here. So that camera is bringing audio in itself, and I can't have that. So what happens is the audio comes into the Blackmagic, and then it brings it in twice. So it's all good now. So let's talk about feeders. Feeders is it's a relatively short article, but we're going to end up migrating over to Article 100 for some terms, 240 for. Do I look like a sound engineer? No, I am not either. I'll tell you what, I had the echo earlier, and I'll tell you, I'm not a sound engineer. I'm not good at much, but I can organize a little thing going on here, but I'm trying. So, but we got it handled. So Article 215 is pretty short article, but you have to understand what the definition is of a feeder. And I'll tell you that a lot of people get this wrong. It should not be echoing. I should not be echoing. You should be, you're probably looking at a little bit older of a video. You're probably in a lag. So the definition of a feeder, but I play one on TV. The definition of a feeder is all circuit conductors between service equipment and the final branch circuit overcurrent protective device. So it's all circuit conductors between service equipment and the final branch circuit overcurrent device, the source of a separately derived system and the final branch circuit overcurrent device, and other power supply source and the final branch circuit overcurrent device. Now, what I've had people say in the past is you have to have a branch circuit overcurrent protective device in the picture, and you do. But remember, it's not the overcurrent device that's protecting the branch circuit. Branch circuit overcurrent protective device is a defined term in the National Electrical Code. So let's take a look at what the branch circuit overcurrent device. Now, we shortened this one. We just call it a branch circuit overcurrent device. It's a branch circuit overcurrent protective device, and it is a defined term. Now, here's the issue. And we're fixing it in the 2026 code cycle. You're right, Steve. Definitions of terms are terminology is critical to our success in this picture. A device capable of providing protection over the full range of overcurrents between its rated current and its interrupting rating for the following. So it's a device that protects for the full range of overcurrents. And it says, though, between its rating. So if I have a 20 amp circuit breaker, the rating of a 20 amp circuit breaker is 20 amps. So this device has to provide protection from 20 amps through its interrupting rating. And if it's a 22,000 amp interrupting rating, it has to provide protection from 20 amps to 22,000 amps. And I'm talking to the microphone like it's a thing. I'm looking at the microphone. I don't know why. But now, it says that it protects services, feeders, branch circuits, and equipment. And I got to break out the equipment. So it protects those four items: services. And remember, if you look at the definition of what a service is, it includes a lot of different components. Feeders, we just saw what the definition of a feeder is. It's everything between sources, and we're going to talk about those here in a second. And the final branch circuit overcurrent device, which could be another feeder. It doesn't have to be a branch circuit. It doesn't have to be the beginning of a branch circuit. Make sense? So it's all the conductors in between. Let's go back real quick. All circuit conductors between service equipment and the final overcurrent device, the source of a separately derived system and the final overcurrent device, and an other power supply source. So right now, what we're trying to help you understand is that when we say a branch circuit overcurrent device or a branch circuit overcurrent protective device, we're not talking about a branch circuit. A branch circuit overcurrent protective device can protect a feeder, it can protect a service, it can protect a branch circuit, it can protect equipment. So it's a very generic term. So be mindful of that. So now, overcurrents are your overloads and your short circuits and your ground faults. Now, you may say, hold on, Tom. We said that a branch circuit overcurrent protective device has to protect from all overcurrents. But remember what it said. Over the full range of overcurrents between its rated current. So if it's a 20 amp breaker, I can have a ground fault current, which is an overcurrent. Or it can be due to overloads, can be due to short circuits and ground faults, but the ground fault current has to be greater than the rated current of the device. Makes sense. So currents that exceed the ratings may be accomplished by some equipment and conductors, so accommodated. So here's the thing. Remember that in some cases, I can take a temporary overcurrent. I can take a temporary overload as long as it's not persistent. And if it is persistent long enough, I need to make sure that the device, the overcurrent protective device, clears the fault before damage occurs. All right? Now, in the definition of a feeder, it says all circuit conductors between the source of a separately derived system. Well, what's a separately derived system? It's a defined term. A separately derived system is an electric power supply output other than a service. It has no direct connection to circuit conductors of any other electric service, any other electrical source other than the bonding. So examples. Here's an example. Transformer. When I put a delta Y ground transformer, now a auto transformer has common windings between line and load. That would not be a separately derived source. Delta, delta, delta Y ground, delta Y, 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 all of those different configurations where the cores are separate, those are all separately derived systems. An other power supply source and the final branch circuit overcurrent device. Well, what are other branch? It's not a defined term, but a generator would be an other supply source. A generator could be a separately derived source, but it depends upon how I bond and ground it. Okay, if I put a ground rod in this device, at this piece of equipment, and I bonded the grounded conductor with the equipment grounding conductors, with the grounding electrode conductor, and I established a separately derived system, then yes, that could be a separately derived system. But typically this is a non-separately derived system. Hold on. Dan, I got to get your first one first. Recently, for some reason, hold on. Can I move this? There we go. Here, you know what I'm going to do? Let's go back to me. Recently, I had a conversation regarding 23085 and how it was, for all intents and purposes, copied over to 225.41. 225 is your outside feeders and branch circuits. Regarding emergency disconnects for 1 and 2 family dwelling units fed. Okay, so I know what that's about. Let's see what's your next comment. By a feeder, once again demonstrating the importance of definitions, service entrance conductors versus feeders. Very good point. Yeah, understanding the separation there, and we're going to talk a little bit about the things that we did for that emergency disconnect in outside feeders and in feeders, so thanks for that. All right, so me and monitor. I guess that's okay if I do that, right? So let's turn that one off. All right. So this is one example of a separately derived source. There's a generator again, another example of a separately derived source. Now this is, I would say this is kind of controversial. The conductors in a PV system meet the definition of a feeder. But they recently added, and I'm going to bring it up over here, they added, I'm going to log into NFPA link over here. So give me 1 second, fill in my password. It's got to look at my face. So they added a, where's the power for this? I'm good. In 705, I'm going to go to 705. Boy, I had this iPad was set up from our discussion, about disconnects. So in 705, in fact, in Article 100, in Article 100, I believe they defined in the 2023 code, they defined a power source output conductor. Let's take a look at that. Power source output. So they have a definition of a power source output conductor, and it's defined as the conductors between power production equipment and the service or other premises wiring. So they sort of relabeled what we know as the definition of a feeder. So you have to be careful when you're looking at PV systems. It looks like a feeder. It smells like a feeder. It meets the definition of a feeder, but they elected to redefine it as a power source output conductor. So that means for those conductors that are between power production equipment, which, I mean, even on that previous slide of a generator, the generator is a power production equipment. So the unprotected conductor from the terminal of the generator to the first overcurrent protective device, the way that's defined, and now this is a CMP4 thing, but it's not just 705, so this can be anywhere. And I told him I was going live at 12 o'clock, and yet he calls anyway. I think he was purposely trying to sabotage me. Anyway, I hate people like that. Anyway, power source output conductors. Power source output conductors is a challenging term in many different ways because the conductors coming off of this power source here are feeders. They are not to be used as a power source output conductor because it says the conductors between power production equipment and the service or other premises wiring. It's a term that presents a challenge for us, but we've got to move beyond that and move into feeders. So just keep in mind, the moment you get into a code panel for purview, we have different terminology. And we have to think about that from a perspective of the application of when you're in and you're not in Article 215. Now, the scope of 215 covers the following for feeders not over 1,000 volts AC or 1,500 volts DC. Keep in mind, in the 2023 code, it's Part 3 of Article 235. That addresses the medium voltage feeder application requirements. So we're going to be looking at installation, overcurrent protection, minimum size of conductors, and the minimum ampacity of conductors. All right, does that make sense? Okay, let's move on. Minimum rating and size of a feeder. So you have your general requirements in A, and let me just call up. I'm just going to bring up. See, now I can have my iPad. So this is the nice thing about NFPA Link and having an iPad. I can bring up the language over here so I know what I'm talking about. So if you look at 215.2, A are your general requirements. B is your grounded conductor. They talk about the sizing of the grounded conductor. That's your, what we quote unquote neutral, but we call it a grounded conductor because it may not be a neutral point. And then you have your ampacity relative to service conductors, and we're going to take a look at that. Let's take a look at some comments first. Dan, you know what, Dan, you're okay. Squirrel, that's okay. That's perfectly fine. I'm good with that. Robert from Omaha, thanks for joining, buddy. Greetings. Couldn't get connected. Thank you, sir. You always have kind words, and I really appreciate it. How does that fit in with 705.12? So, you know what, Dan? I can do a whole nother section on 705. In my opinion, those are all feeders. They meet the definition of a feeder. They smell like a feeder. They taste like a feeder, and you should taste those next feeders. But 705.11 and 705.12, so especially 705.12, whole different topic, and I'll look forward to talking about that. Yes, 705.12a. I'll see if I have some time at the end of this to hit some of that. Generators, conductors are also power source output conductors. Well, Felix, I mean, they meet the definition of it. A generator is a power source. I don't agree with it. It meets the defined terms, but we treat them like feeders. They are feeders. You wouldn't go anywhere else other than 215 to understand what to do with the generator conductors that are powering the system, because they are feeders. Panel 13 understands the definition of a feeder. Panel 13 understands Article 215. Apparently, we have some challenges over in Panel 4. And the principal, I can't even say the principal reason, is because in a PV system, they're a source, because in the generator, that's a source too. Anyway, they are feeders. What about conductors going to a load bank setup? Those are feeder conductors. Well, a load bank setup. When you say a load bank, let's think about that. If the load bank has overcurrent, if I have overcurrent, if I go from a breaker to another, say a panel board, that then supplies a load bank. I'm not sure what you mean by a load bank. What do you mean by a load bank? I need that information. Load bank. Give me a little bit more to go on. When you say load bank, describe the circuit for me, and then I can help you understand if that is a feeder or a branch circuit. If you have a overcurrent device and then you go to a load bank and the load bank is a load, then that's a branch circuit. That's not a feeder. And your last overcurrent protected device is a beginning of the branch circuit. If you have another overcurrent device ahead of that load bank, then that's a feeder. So hopefully that helps a little bit. So 215.2a, general, is where we get into doing your ampacity for the conductors. And this is, remember, a feeder. This is a feeder circuit. You have two things to think about when you're dealing with conductors. The first thought process is, when you're dealing with a conductor, you have the ampacity of what the capability of the conductor itself. How much current can a conductor carry under a specified condition of use? And in 310.16, there's a table that gives you the conditions of use at the top. Okay, that's 3 current carrying conductors, whatever. And then, boy, I wish I had a paper book. I have this book. Anyway. And then, once you understand the conductor itself, then from a circuit perspective, it's going to have a beginning and an end. It's going to start and originate, probably in equipment, and then it's going to end possibly in equipment, or it could end in a load. But we have two things to think about. One is the capability of the conductor itself, and second is the limitations placed on the circuit based upon the weakest link, which is one or both ends of that conductor, the equipment within which that conductor is terminated. It could be on a circuit breaker, it could be on a bus bar, or whatever it is. You cannot, so, okay, we got a little bit more on this load bank. The load bank is used to test the generator. It has an OCPD on the generator, which, yep, you cannot tap the load bank test conductors to the line side of the generator OCPD, direct to the generator. So if it's direct to the generator, when you're testing that generator, if you're testing the generator temporarily, that's a branch circuit. Right? Because if it's a load, if that is you're talking about a test scenario. It's not normal operating conditions. So you're not in a permanent, you can't look at something, in my opinion. I can't say, well, I'm going to test this. You're under test conditions, and under test conditions, the code sections are going to change. So if you want to size, if I was going to put a load bank of resistors or whatever on this generator to run a test, I can't exceed the ampacity of the conductor, and I can't exceed the ampere rating. So I would have to make sure that the circuit is adequate for running that load test, because now it's just basically a generator breaker, a conductor, and a load. So that would be a branch circuit at that point for under those test scenarios. That's the way I would look at it. It's basically you're running you're doing something that is not a part of the permanent wiring. But when that generator is in place, it is a feeder. Okay, so you have to make sure that the conductor and all of that equipment is sized as feeders. But under that specific test scenario, it's an oddball. I mean, you have to just make sure that you're not going to overload the conductor. If there's a short circuit in your load bank, that the circuit breaker is going to take that out. But again, it's under test scenarios. So I don't know what else to tell you. Dan says, what really gets this twisted is that for the most part, feeders contain two-phase conductors, a neutral and an equipment grounding conductor. Two-phase conductors. Oh, two-phase conductors, a neutral and an equipment grounding conductor. But a generator that is not a separately derived system won't have an equipment grounding conductor. You always have an equipment grounding conductor, Dan. In my opinion, you're going to have to bond everything together. So you still have to bond everything back out to that generator. That's a separately derived system. You have to follow Article 250, and you may not have a neutral. You'll still have a neutral, and then you'll have a supply side bonding. I'm not sure what you mean by you won't have an equipment grounding conductor. You're saying that between the generator and your panel board, there's no bonding going on? I'm not sure if I agree with that. You'd have to help me understand that one. Those conductors need an overcurrent device. Yes, absolutely. You have to be downstream of an overcurrent protected device. I would agree with that, Robert. Yep. And that is your short circuit and your ground fault protection. Because if your load bank has a problem, you need to have it protected. I would agree with that. So does power source conductors include UPS, all are converting a source of energy. So that's the roommate 625. I would argue, yeah. Yes, it does. I would treat them as feeders, but they meet the definition of a power source output conductor. And if you are doing interconnected systems, you're in 705. You're not in 215. You're in a different article. Different article, different day. That would be a redundant neutral in a non-separately derived system. That would be a redundant neutral. In a non-separately derived system, you don't bond the neutral and the equipment grounding. So all you're doing is bonding the equipment. So it's not a neutral. It's not a grounded conductor. It's a grounding conductor. It's a bonding conductor. Your neutral that's coming from the generator is not connected in the generator and bonded to the equipment. It's floating. It's isolated from the equipment. The bonding is all occurring in your service equipment. All right, so what we do to determine the minimum rating and size of a feeder is we follow A. And I don't know why that keeps coming up. Education. Turn that off. Actually, how do I delete it? X. Boom. Okay, that's gone. All right, so what I do in A is I have to do two calculations. One, I do the continuous and non-continuous loads. And two, I do the ampacity adjustment or correction factors, and whichever one gives me the larger ampere rate ampacity that I need, that tells me what will suffice for the conductor itself. I haven't determined the overall ampacity of my feeder until I consider 110.14, which is the equipment within which I'm landing a conductor. So what I do is the first step is you take your continuous and non-continuous loads. You do 1.25 times the continuous, and you add the non-continuous. And if that comes up to, 150 amps, then you put that over here and you say, okay, I got 150 amps. Then you forget about the continuous loads at 125%, and you simply adjust for the correction factors, which is based upon the conditions of use. Now that would be your how many conductors you have in a raceway, and then temperature. So you adjust based upon those conditions of use, and then that tells you the current. Now, if we said it was 150 for A1, and let's say it's 175 for A2, then you need a conductor that can handle 175 amps. So then what we do is we go to 310, and we find so we said 175 amps. Let's do that. Let's go to 310. 310.16. I go to 310. I go to 310.16. 310.17. 310.16. And I said I needed 175, right? So I'm going to do expand table. 175. Oh, and I can pin the header. Just learned that not too long ago. And since I'm dealing with a 90 C insulation, I scroll down and I find that I'm into a 2-aught conductor, which can handle 195 amps. Now I said that my largest was 175. In this case, if I'm landing in equipment that's 75 degrees C rated, I use the exact same table. I ignore the insulation ratings at the top. So don't get yourself bogged in that you're using this same table for a different reason. You're using this table for the reason you're using this table to satisfy 110.14, the terminations. And if I am in 75 degrees C equipment, I'm going to look at the 75 degrees C column, and I at least have to have 175 amps. And it just so happens that because I was at 175 amps and I picked a 2-aught conductor, which is good for 195 amps, in the 75 degrees C column, it's good for 175 amps. So my conductor does not have to change. I would use a 2-aught conductor. Now, if my amp if my ampacity had to be 170, then a 1-aught conductor would be good for 170 amps, but at 90 degrees C. But when I look at my equipment, which is 75 degrees C, and I look at the 75 degrees C column, I realize that a 1-aught conductor for 75 degrees C equipment is only good for 150 amps. I would have to increase to a 2-aught conductor to be able to handle 170 amps. Capiche? So it's a process, and we can't forget that process. Now, if we're in the standard conditions of use, then I'll probably fall back on the 125% number. But I have to do both calculations. I do the 125% times the continuous. I do the 125% times the continuous plus the non-continuous, and I ignore the conditions of use, do that calculation. Then we do a calculation based upon just the conditions of use, and I ignore the 125%. Whichever one gives me a larger number, then I go into table 310.16, based upon the insulation rating, 90 degrees C, find my conductor size. Then I look at the equipment, 110.14C, and if it's 75 degrees C equipment, or if it's 60 degrees C equipment, whatever, or it could be 90 degrees C equipment. Then I go back into table 310.16, and I look at the appropriate column, and I make sure that it is equal to or greater than, for that same conductor size that I just picked, that the ampacity for the circuit for that equipment has to be equal to or greater than that number that I needed. I hope that makes sense. So that's what A is doing for us in 210.15. So that's A. Now, B is your grounded conductor. What this does, it points us over to 250.122. Now, 250.122 is going to introduce, now remember, this is a feeder. I got to go to chapter 2. 250. This is where, oh man, oh boy, I'll tell you what. 250.122 gets me yawning. It's boring. It's just grounding and bonding, and it's so non-controversial. You know what I'm saying? 250.122. Where is it at? 250, 119, 120, 122. Size of the equipment grounding conductor. Now, what 215.2 tells us is that the size of the feeder circuit grounded conductor can't be smaller than the equipment grounding conductor size required by 250.122. So that tells you just go to 250.122 and follow the rules there. We did not reinvent the wheel for 215. Point you over to 215. 250.122. And then in 250.122F, conductors in parallel, it says, shall not apply where grounded conductors are run in parallel. All right, so let's take a look at 250.122A. Tells us, this is the general requirements. 250.122A tells us copper, aluminum, or copper-clad aluminum grounding conductors. That's grounding conductors. So it wants the grounded conductor to be no smaller than the equipment grounding conductor size. That's interesting. So I size the equipment grounding conductor, and then I make sure that my grounded conductor is the same size or larger. .122B is when I have the increase in size of my ungrounded conductors. So you got to be mindful of that. Oh, man, this coffee. So look at that. Oh, my Colombian roast. So I have to think about increasing the size of the equipment grounding conductor if I increased the size of my ungrounded conductors. It says if ungrounded conductors are increased in size for any reason other than 31015B or C, that would be your conditions of use, etc. That's your temperature and your number of conductors in a raceway. So if I did it for voltage drop, for example, then I have to increase the size of the equipment grounding conductor proportionately. That would mean that I have to increase the size of that grounded conductor proportionately as well. That is for fault current. Robert, what's Robert saying? That is for fault current, the comparison of both. Yeah. I don't know if you're talking about increasing. Are you talking about 250.122? I'm not sure. Please give me a reference of the section that you're speaking to, because I'm not sure if you're talking about the parallel conductors or if you're talking about increase in size, 250.122b. So anyway, or you can engineer a solution. So if I have, for example, ground fault protection of equipment, or if my ground fault current exceeds, if I have a 200 amp feeder, as long as my ground fault current exceeds 200 amps, I don't need to increase the size of the equipment grounding conductor. I don't need to increase the size of the grounded conductor. Makes sense? So remember what the exception says: equipment grounding conductors shall be permitted to be sized by a qualified person to provide an effective ground fault current path in accordance with 250.4A5 or B4. And if I think about what 250.4A5 is telling us, is that you have to basically open the overcurrent protective device on that ground fault current. So if I have a 200 amp overcurrent protective device, my ground fault current has to exceed 200 amps. That's it. So if I can do that analysis, then I don't need, if my ground fault currents are good and strong. Now, if I have a very, very long conductor run, then I may need to increase the size of my equipment grounding conductor, but in my opinion, I still may not trip the overcurrent device. I may need to put ground fault protection of equipment in there as well. Neutral versus the equipment grounding conductor. Yeah, I would agree with that statement, Mr. Robert from Omaha. I would agree, senor. Oh, there we go. Get that out of the way. All right, so... Okay, so let's go back. Nihad. I mentioned that during a previous live, using a Class D GFCI may dictate the increase of an equipment grounding conductor size to ensure that the voltage to ground is not more than... yeah. So which is a completely different... So if you're applying a Class D special purpose GFCI or a Class D GFCI, yeah, you have to really look at the size of the equipment grounding conductor, and absolutely. But if I'm doing just ground fault protection of equipment, I don't need to worry about that. I'm not sure, but I believe there will be no need to increase the size of the ungrounded conductors. But here's the thing. Based upon this section, Nihad, it says the size of the feeder circuit grounded conductor must not be smaller than the equipment grounding conductor sized by 250.122. So if I have to increase the equipment grounding conductor for the reasons that you're saying, and not because of 250-122, then I would agree with you. I do not have to make the grounded conductor increase in size because of that increase in size of the equipment grounding conductor. So good point that you may find a scenario where the equipment grounding conductor exceeds the size of the grounded conductor, as long as it's not because of 250.122. Good point. I like it. I like it a lot. All right, so you got to remember 250.122. So let's take a look at, okay, those are all of the conditions in 250.122. So let's take a look at 215.2. Minimum rating and size. This is the ampacity relative to service conductors. 215.2. This is 215.2c. So what this says, the feeder conductor ampacity shall not be less than that of the service conductors, where the feeder conductors carry the total load supplied by service conductors with an ampacity of 55 amps or less. Let's read that one over again. The feeder conductor ampacity shall not be less than that of the service conductors, where the feeder conductors carry the total load supplied by the service conductors with an ampacity of 55 amps or less. So that tells me that the conductor, if the conductors are 55 amps or less, man, that's a tough one. So if my service conductors, say I'm going to a 400 amp panel board, if my feeder does not have to be larger than the service entrance conductors, let's read that again. The feeder conductor ampacity shall not be less than that of the service conductors, where the feeder conductors carry. You know what, Kawasaki, I'm the same way. When does that happen? It says service conductors have an ampacity of 55 amps or less. The feeder conductor ampacity shall not be less than the service conductors, where the feeder conductors carry the total load supplied by the service conductors with an ampacity of 55 amps or less. So if I've got service conductors that are 800 amps and I'm going to a 400 amp panel board, then I can have a feeder that is less than an 800 amp service, even if it's carrying the entire load of the service. So let's say I have a feeder and it lands on a service over current protective device, and the service conductors coming to that service over current device are 800 amps worth of conductor, and I'm going to land it on a 400 amp device. I could do that, and the feeder can be sized at 400 amps, which is less than the 800 amps of the service. But if my service was less than 55 amps, or if it was 55 amps or less, then I could not size my feeder at less than that, which, man, I don't understand why C is even there. I don't get it. I just don't. Because the service conductors have to have an ampacity of 55 amps or less. So I'm with you, Kawasaki. I'm with you. Yeah. All right. 215.3 just tells us that I have to protect those feeders based upon Article 240. And now this, and I'm torn on this one. It says Part 1 general requirements. I have to protect this based on Part 1 general requirements. In Part 1 of Article 240, you have your scope, you have your reconditioned equipment, you have other articles, you have your protection of conductors, 240.4. And then there is the so it's Part 1. So that would mean protection of conductors is in 240.4. And this is where you have your overcurrent devices rated 800 amps or less. Can you go to the next higher? All that good stuff. You have overcurrent devices rated 800 amps or less. Then you have your small conductor requirements. You have your tap conductors. Tap conductors shall be permitted to be protected against overcurrent in accordance with 210.19 C and D. That's for house and ranges. You have your fixture wires. Location in a circuit is 240.21. So that'll get you into your feeder taps, 240.21. You have your busway in 368.17b. You have feeder and branch circuit busway taps in 368 and 17c. That's a different discussion for a different day. And then you have your single motor taps. So this 215.3 overcurrent protection really opens up a can of worms because it points to 240. And you're into Article 240 Part 1, which then brings in Part 2, the location in a circuit. And you get to your feeder tap requirements, provisions. So you have to be mindful of your feeder taps as part of 240 as well. Don't forget to like and subscribe. Absolutely, Laurel. Please hit that thumbs up. Make sure you subscribe to IAEI's YouTube channel. And we are growing by leaps and bounds. We're growing like 500 followers a month. So if you're watching this, whether it's live or it's not, please subscribe to the YouTube channel. You're going to be a part of something great. We are coming up with a lot more material for online experience. So please don't forget to contribute by subscribing. So it says the overcurrent device must be sized for the feeder must be sized such that when the feeder supplies continuous loads or any combination. So what this is telling you is that your overcurrent protected device, unless it is rated for 100%, you have to multiply the continuous loads by 125%. And that's not a condition of the conductor, that's a condition of the overcurrent protective device itself. Okay? There's your exception for 100% rated equipment. Now, I just had a phone call on 100% rated equipment yesterday, actually. Gentleman calls me up and he says, hey, look, he says he has an installation where they've done the load calculations and they've exceeded this 80% rule for the overcurrent protective device. And so now he's looking at just buying a 100% rated circuit breaker. Here's the problem with that. When you're dealing with 100% rated applications, it's not just about buying a 100% rated circuit breaker. You've got to think about the equipment that within which it is installed. If you do 100% rated circuit breaker, the panel board or switchboard has to be also 100% rated. So in the case for the call that I had yesterday, the customer had, or not the customer, well, it wasn't my customer, it was someone else's customer. The application had a panel board that they wanted to just put a 100% rated breaker in, but you've got to make sure, you've got to look at the panel board, and if it's if it can be used at 100%, because remember, 100% rated, what we're talking about is temperature. You're worried about the temperature rise inside the assembly. So if it's a 100% rated circuit breaker, that's good, but your equipment that you're placing it in has to be 100% rated. It may be some panel boards require a higher density copper bus installed inside the equipment. Your equipment may need to be of a larger enclosure to handle the heat, the additional heat that's going to be generated using the equipment at 100%. So if you made a mistake in your load calculations, don't think that just by replacing the overcurrent protective device, you have solved your problem, because you may not have solved that problem at all. Make sense? So be careful of that. And we can use this exception, but it's not just about the overcurrent protective device. It's the equipment within which that overcurrent device is installed as well. So we got feeders with common neutrals. It is 1 o'clock right now, so I have exceeded everything that I can do on an IAEI News Live. So stay tuned, because we will be growing our station here, our IAEI YouTube channel. What's this say? Bus shelters grab power from overhead transformer, and the service conductor can be less than 50. There we go. Well, now we know. And that's why we have to have good roommates. And roommate 625, you're a good one. So thank you for enlightening us on that one. Very good. Very good. I really appreciate that. And Laurel, thanks for your insights. Much appreciated, Laurel. Thank you for joining in. We really appreciate you, and we appreciate everybody out there. Nihad, Kawasaki, Roommate 165, Dan, Felix Sandoval. I know Robert from Omaha was out there as well. David Englehart in the house. Steve Specker, whatever. I love you, brother. You're the man. And Nihad El Sharif, of course. So thanks, everybody. I hope everybody has a wonderful Thanksgiving. Gobble, gobble, right? That's the key. And I hope that we all have a very good Thanksgiving. Don't eat too much turkey. Thanks for everything and joining in today. I know this is Thanksgiving week, and probably a lot of you have taken off this week. I know I did, but I wouldn't miss an IAEI News Live if it meant not being able to talk to all of you. So thank you very much for joining in. I appreciate all that you do, all that you do for our safety and for IAEI. If you're not an IAEI member, you need to become one. Please don't forget, join IAEI. Also, subscribe to the channel. We'll increase safety together, and we'll increase our general knowledge. I'll continue feeders, and we'll do some examples maybe next time. Thanks. Happy Thanksgiving. Stay safe. And please, stay healthy. See you next week.